Live. Okay, I think we are live. Yeah, let me see if I can hear myself clearly. Yep, I can hear myself. So, hey everyone. Uh, so what's the agenda, right? We'll discuss about the agenda, but just give me some time. Let other join in as well. Keep the chat open meanwhile. Okay, five of us are here. Okay, so what is exactly the agenda here, right? So you all might know, like when you're preparing for your interviews, let's say you want to give you an Amazon interview, right? And there are, like, when you visit Geeks for practicing, uh, let's say 700 questions, right? And you kind of feel lost. Hey, how am I going to do these 600 questions, right? um, and it's difficult sometimes, but like doing it alone is difficult, to be honest. So what we have decided here is, let's actually get you in a habit. So we will be having around 29 classes on this, where every day we'll be discussing some problems, like around 1 to 2 problems, and also we'll be giving you homework, right? So not every day, like the classes will be around let's say 3 times a week or 4 times a week. But again, like we'll be giving you some problems for your practice, as well as we'll be discussing some problems live. And yeah, after that, basically we'll be in a habit of solving these questions. So just think, like in 29 days you basically will be solving around 29 into, let's say, 3 problems or 5 problems daily. Not daily, like basically in a stream, 2 problems will solve, and 3 problems, let's say, for your homework. So around 29 into or 30 into 5, right? Around 150 problems will solve in just 29 days. So you will be in the habit of solving your problems, and then you can basically take from there. And as well, we have chosen the problems in such a way that they're really good problems, so that and also they're not repetitive, right? There is a lot of repetitive questions as well. So we have made sure that the questions are not repetitive, and we have made sure that the repetitive questions are added for the practice. So yes, you'll be solving around 150 unique, not unique, but again, like very different questions. And yeah, that I think that's a good thing, right? So that's mostly the agenda. So today we'll be discussing about 2 problems again. Like the problems are check for BST and check for balance tree, and after that also there are some problems added for your practice. So you can find all the problems in the description. So every day when you're joining the stream, make sure you check the description, because that's where you will find all the problems for practice, as well as the problems that we'll be discussing today, right? So that's about the agenda. So we'll get started. Right, we'll get started with our first problem. So the first problem that we'll solve today is check for BST. It's a pretty simple problem. Like today we have chosen easy problems, definitely, like it's the start. So check for BST, what it tells is you're given the root of a binary tree, right? You're given the root of a binary tree, and you have to check whether it is a binary search tree or not. By the way, just to be clear out here, I'm not going to discuss about the details about things like what dynamic programming is, what binary trees are, what are the various algorithms around binary trees, and these things. I'll not be teaching you anything, right? What I'll be doing here is I'll be solving problems with you, and I'll be explaining you how to think about those problems. So it will be more of problem solving session. So if you don't know about some things, make sure that you are ready. Like, you're only attending the sessions when you're ready with all the things. You have knowledge about all the things, but you're facing problem with solving a lot of problems, right? Or getting the logic of the problem. So I'm here to help you with those things, not to teach you anything new, right? So that's not what this series will be about. So okay, so you're given a root of a binary tree. Again, I'm assuming that you already know what a binary tree, and you already know about what a binary search tree is as well. But again, we'll touch on binary search tree in a short way. So you have to check whether it is a binary search tree or it is not a binary search tree. So here it is considering binary search tree cannot contain duplicate, like it doesn't have duplicate nodes, right? Whatever tree is given to you, it doesn't have any duplicate nodes. It is considering that thing, right? The BST is also defined here. That's good. A BST is defined as the left subtree of node contains only nodes that has keys less than the current node key. So all the keys in the left subtree of a node will have the values less than the current node value, right? Similarly, the right subtree of a node will only contain keys, that is, they will only contain values that are greater than the current node's value, right? So that's basically a definition of a binary search tree. So if all the nodes individually satisfy this property, that the left subtree has all the keys smaller and the right subtree has all the keys greater than the current node's key, in that case it's a binary search tree. So for example, here if we see, Bhaiya, do you have these classes daily in this time? Not daily, it's maybe 3 to 4 times a week. You'll know about the classes, just follow this channel. I think for this week, we'll have today, tomorrow, and day after tomorrow. But from next week, we'll have 3 days. I'm yet to decide on the days. Maybe we'll finalize on the days and keep it maybe the same, like Wednesday, Thursday, and Friday. We'll figure that out. But yeah, like just for the first 2 weeks, maybe just follow the channel and look into like whenever you're seeing a class scheduled, just the time will be same, right? The time will be same. There should not be any changes on the time, but the like the dates might actually vary. Like it, some days I might take on Monday or Tuesday, but yeah, we'll try to finalize on that as well. Okay, so yes, so we are given a tree here, so 2 1 3, right? So if you see, let's go through all the nodes one by one. 2, hey, in the right left subtree of 2, what is there? Only 1 is there, right? Is the value of 1 less than the current node's value, that is 2? Yes, it is. So it's a this part is valid. Let's go to the right subtree now. What is there in the right subtree of 2? It is 3. Is the current node's value, sorry, okay, is the current node's value, that is 3, that is 2, less than the right subtree, all the nodes in the right subtree, their values? So the all the values, there is only one of them, that is 3, so it is greater, 3 is definitely greater than 2, so it is a valid binary search tree, right? It is a valid one. So here if we see 2 7 6 5 9 2 6, is it a valid binary search tree? Let's see. For 2, all the nodes, what are the nodes on the right subtree? On the left subtree there is nothing, so we don't have to worry about. On the right subtree, what are the nodes? The values of the nodes: 7 6 5 9 2 6. Are all the values greater than equal greater than 2? So if we see, it is actually not greater than 2, because there is a duplicate. So yes, there are duplicates possible. The tree might contain duplicates, but again, like, we'll consider a binary search tree will not contain any duplicates. So in that case, we should return false. But again, right, that's actually, I think, not the reason why we are returning false. We are returning false mostly because for 7 on the right subtree we have 2, right? So that's why also we can return a false here. Okay, so again, like, I think the test case here is wrong, because it is told that we are considering not duplicate, cannot contain duplicate nodes. Okay, they cannot contain duplicate nodes. Maybe they contain same values, I'm not sure, but yeah, like, not duplicate nodes, right? Okay, yeah, that makes sense. Like, the left and right child will be different, something like that maybe. Okay, so that is given to you, so you have to tell what is the, if it is a binary search tree, right? How can we do this? So what is the complexity that is given to us? It's order of n, and height of the binary search tree is the space complexity. Okay, so let's actually define quickly again what is a binary search tree, right? So if I have, let's say, if I have something like a 4 here, right? 4 on the left I have 2, on the right I have 3, on this left I have 1, I have 5, I have 6, right? So if I have a tree like this, right, it is a binary search tree. Why? Just check for every node. For this node, on the left subtree, we have all the nodes that are smaller, like all the values are smaller than 4. On the right subtree, all the values are larger than 4. That is 5, 6 are larger than 4. So 4 is valid. Let's come to 2. For 2, all the elements on the left are smaller than 2. All the elements on the right are greater than 2, right? So only 1 and 3 are there, so they are smaller and greater respectively, so it's valid. For 1 and 3, they are the leaf nodes, so we don't care about them. They are anyways in a balanced state or binary search tree state. For 5, all the elements, there is no left element. all the elements on the right are greater than 5, which is indeed true. 6 is greater than 5. So that's why, as all the nodes are satisfying the property of a binary search tree, so we will tell that this tree is a binary search tree. However, let's say, let's take an example here. So let's say we have something like 2, and here we have 7, right? Here we have a 7. So for 2, although it is a binary search tree, for 2 it is a binary search tree, right? On the right there is a greater node, on the left there is a smaller node. But for 4, it is not a binary search tree, because on the left there is a 7 which is greater than 4, so it cannot be there. So that's why it is not a binary search tree anymore. And indeed, this example actually tells us that we cannot follow a greedy like approach, that where you just check for every node if it is a binary search tree, right? So if you do like that for 4, if you just greedily check, hey, is 2 less than 4? Yes. Is 5 greater than 4? Yes. So it is 4 is in a valid state. Again, you go to 2 and check for 7 and 1, and you see that it's in a valid state, right? So that approach will fail, because if you see from 4, you are not able to identify like that 7 is actually greater than 4 but is on the left subtree, right? So you have to have a better approach. So what can we do here? What we can do here is, so when we will go for a DFS like approach, right? We'll definitely go for a DFS like approach. But what we'll do is we'll restrict the values, right? We'll, for every value we will check, can it have this value, and if it can have this value, we will restrict the values for the child nodes accordingly, right? What do I mean by this? So when I start off at 4, right, I don't have any restriction with me. 4 can be in a free range yet, because I haven't seen the tree yet. So 4 can be anything, right? So it is in a free range right now. Let's say minus infinity to infinity. It is in a free range. Now when I get 4, when I move to the left subtree, what do I know? All the elements on the left subtree should be less than 4. So that means I am fixing all the elements on the left subtree will be within the range minus infinity to 4, and it cannot be 4, right? Or we can in fact include 4 as well. That also works, but we don't have duplicate keys, so we'll not do that, right? So minus infinity to 4, or we can have a closed interval as well. So all the elements should be less than within this range minus infinity to 4, right? They cannot be greater than 4, otherwise it will not be a binary search tree. Now we see a 2. When we move to the left, we know that all the elements on the left should be less than 2 as well, right? So it will be within the range minus infinity to 2, anything. Now when we move to the right subtree, what is the condition that we have? It should be greater than 2, because we are moving to the right subtree. It should be greater than 2. So the left, it should be greater than 2, but again the condition was it should be less than 4 as well. So it should be less than 4. So this is the range in which it can the value can be here, right? This is the range in which the value can be here. Now we will come back here again, right? Now when we go to the right, we know it should be greater than 4. It should definitely be greater than 4, greater than equal to 4. So for 4 to infinity, it can be any value. Now when we move to the right again, now it should be greater than 5, because it is on the right subtree of 5. So 5 to infinity, like that. So this is how we'll do, and for every node we'll validate if the node's value satisfies this property. If we come here, we see that 7 doesn't lie in the range. 7 doesn't lie in the range 2 to 4, so it will return an invalid. It will return that it is not a binary search tree. So that's how we'll do this. It's pretty simple actually, right? It is pretty simple. There's nothing to like nothing extra to do here. So what we can do here is, so we'll create a helper method for us. So let's create in a private section. So bool check bst. Let's call it check bst. It will contain the current node that we are at. It will contain the minimum value and the maximum value that it can have, right? Minimum value and the maximum value. So if root equals to null, sorry, if current equals to null, then we will return true, right? Now if current node's data, if it is not null, so it is a valid node. If current node's data is less than minimum, or current node's data, right? If current node's data is less than minimum, let's go to full screen, or current node's data is greater than maximum, right? Is greater than maximum, then we should return a false, right? Otherwise, what we should do, we'll go to, so return check, we'll go to the left subtree now. So current of left subtree we are going. In left subtree, what do we restrict? We restrict the maximum value, right? We restrict that as we are going to the left subtree, the maximum value cannot be more than this. So minimum will remain to be the minimum, but the maximum will be restricted to what? It will be the minimum of whatever is the existing maximum, whatever is the maximum that we have till now, because it cannot be more than that, or the current nodes data, whichever is the minimum, it cannot be more than that value, right? So current nodes data. And because we'll check for both left and right subtree, so and check. Now we'll check for the right subtree, so current nodes right will go into. What do we restrict here? On the right subtree, we tell that all the elements should be greater than this value, right? So we are restricting the lower bound, we are restricting the lower range, so the minimum should be maximum of, like, it should be greater than value. So whatever is the maximum, the existing minimum is maximum or the current nodes data is maximum, it should be greater than the maximum of them, right? So current of data and the maximum will remain the same, right? So that will be it. Now we can just return check bst for our root node. Initially it will be int min to int max, it has a free range, so int min to int max, right? So this should be the code. Let's try to compile it and see if it is working. Meanwhile, if you have any questions, feel free to ask. Okay, it's not working somehow. Why? Root int min int max. Check was not declared in this code. Okay, check bst should be. Check bst and check bst. So let's see if it is working. So it's passing the sample. Let's submit. Okay, let me know if you have any doubts with this. Like, we are basically restricting for every value, we are restricting what is the range in which it can be while we are moving down, right? So we are telling that, hey, as we are moving to the right subtree, it cannot be, it has to be more than this value, right? And again, we already have a minimum limit what the value should be, right? So it should be greater than this value or the maximum of this, right? Maximum of the current value that we have, or that one, or sorry, or the, yeah, I think maximum. Yeah, yes, maximum of the minimum value that we have or the current data that we have, it should be greater than that. So that's how we are doing this. So is this clear with everyone? Let me know once. Is it clear with everyone? Okay, if it is clear with everyone, so let's go to the next one. So it's pretty simple, right? It's a pretty simple problem, I believe. It's clear with everyone. So next problem will be a bit tougher than this, right? So it's also easy, but again, like, it's a bit tougher than the existing one. So what it tells is, it tells us to check for a balanced tree, right? It tells us to check whether a tree is given to us is balanced or not. So what it tells is, given a binary tree, find if it is height balanced or not. A tree is height balanced if the difference between heights of the left and right subtrees is not more than 1 for all the nodes of the tree. So you have multiple nodes of the tree, right? So can you repeat the return statement of check bst? Yes, I can definitely repeat the return statement of check bst. So return statement of check bst, what we are doing, we are first of all validating for the current node if it is a valid value. Now we have to recursively go to the left and the right subtree. Now we are first going to the left subtree and we are checking if the left subtree is a valid bst. So check bst, this validates whether the left subtree is valid, right? Whether the left subtree is valid, because we have already validated, as we are coming here, we have already validated the current node. Now we just have to validate if the left subtree is also valid, right subtree is also valid, then the entire subtree is valid. Basically it's a valid bst, right? So check bst, this validates the left bst whether it's valid, right? So in the left subtree, what do we know? The value in the left subtree should be less than give the current value that we have, or less than the current value. So current of left should be the minimum of so we'll go to the current of left. Now it should be less than the current value, right? So it should be less than whatever is the minimum that we have, the minimum range that we have, or the current value that we have, right? Again, like I think our current value is within this range of minimum to maximum, so I think we can safely remove this mean operation, right? Because it's anyways within maximum, right? So our current data will be within maximum, so definitely we can just go for current data. We can definitely go for current data. Again, here also our current data is definitely more than the minimum limit, greater than equal to, so it will be definitely maximum will definitely take that. So we can just safely remove the minimum and the maximum, right? So we are basically restricting, hey, in the left subtree the value should not be more than the current data that we have. Similarly, here we are restricting the value should not be right, should not be more than this data, sorry, should be more than this current value that we have, because on the right subtree we should have values greater than the current data. So I think this should work. Let's submit it and check it out anyways. Logically it seems it should work, but let's check it out. Yeah, I think it should work. Yes. So yep. So what we are telling is, hey, when we are going to the left subtree, our value should be within this minimum, like our value should be within the range of minimum to maximum, definitely, because all the elements in the subtree should be within the range of minimum to maximum, that is guaranteed. But we are also telling that, hey, our value on the left subtree should be less than the current data, right? So we are updating our maximum, the upper range, to current data. Similarly, for the right subtree, it should be at least the current data, it should be more than the current data. So we are updating the minimum to current data and we are checking, right? So that's how we are doing this. Okay, check for balanced tree. So we are given a binary tree here and we have to check if it is height balanced or not. What do we mean by height balanced? Height balanced tells that the difference for every node, the difference of height between the left subtree and the right subtree, it should not be more than 1. The difference between the left and the right subtree should not be more than 1 for any node. So let's take an example here. For 1, what is the height of the left subtree? 2. The right subtree is 1, so the difference is 1, it is valid. For 10, left subtree is 1, right subtree is 0, so again 1, it is valid. For 5, it is the only node, so it's valid. 39 also valid. So for all the nodes it is height balanced, so that's why it is a height balanced tree. This one is the height unbalanced tree. Why? Because for 1, the left subtree has a height of 2, right subtree has a height of 0, so the difference is more than 1, so it is an unbalanced tree. So this one is also unbalanced tree. For 1, the left subtree has a height of 2, the right subtree has a height of 0, so it is an unbalanced tree, right? So you have to check for height balanced. We'll take another example maybe so that we understand this better, but before that let's understand the complexity consideration here. So order of n and order of h, right? So order of h, because when you're doing a recursion you actually need space as well, right? So that is the space complexity, that you are going across in a single height, right? So at max order of h nodes will be there in the recursion stack, right? So that's why the space complexity given is order of h, and this also highlights that it will be a recursive solution definitely. And anyways, like most binary tree questions are recursive solutions unless you have a threaded one, but again, like, yeah. So let's understand this a bit more. So let's say we have a binary tree, it's not balanced, it's not a binary search tree as well, it's just a height balanced tree. So let's say 2, let's draw any tree, right? 1 4 3 5 7 8, right? And 7 8, yes, 3 5 7 8 and 5 here 9, let's say, and 4 6 7 and 4 11, let's say. So this is a binary tree, right? Let's check for the root node. For the root node, what is the height of the left subtree? 1 2 3 4, we'll take the maximum one, 4. Right subtree 1 1 2 3, so the height is 1, so it is valid. Height difference. For 1, the left subtree has a height of 1 2 3, right subtree has a height of 2, so one difference is valid. For 4, 1 and right has 2, so one difference is again valid. For 3, the left subtree has a height of 2, but the right subtree has a height of 0, so it is invalid, right? It is invalid. So similarly, for 7 it is valid, for 5 also it is valid, for 9 it is valid, for 3 it is invalid. So this is where the invalidation occurs, so we should return false basically, right? So this is the this is what height balance tree is. It should always be within 1. So if we add a node on the right hand side of 3, it will become a balanced tree, right? It will basically become a balanced tree. Yeah. So how can we solve this, right? Now it is unlike the previous question. In the previous question we could restrict on the values, like we could make some values propagate downwards, but if you think about it, here actually it matters how many nodes are below you, right? So how many nodes are below you, that matters. Now one obvious question is, for every node we can find the height, right? So we'll run a DFS. In the DFS, for every node we'll find its height, we'll find the height of the left subtree, we'll find the height of the right subtree, and then we'll compare. But again, that will be a n squared approach, right? For every node we are finding. You might suggest that, hey, let's compute it again, but again, like that will involve space complexity, which we don't have that we cannot have, right? We can have order of h space complexity. So here we need to know from the bottom how many nodes are there at the bottom, right? So that is something that we need to know. And how can we know that? Because in recursion we can send values downwards. How can we send values upwards, right? We don't know about that, or do we? So definitely there is a way to send values upwards as well. So what we'll do here is, we'll do it in a pretty simple way, right? What we essentially want is, we want the height of height of a subtree, right? We just want the height of a subtree. Let's take a private variable here called height, right? This will store the height of a subtree whenever we are computing. Now, first of all, if root equals to null, if we have reached a null, what is the height of the subtree under this? It is 0, right? So we'll mark the height to be equals to 0 and we'll return a true here. It is valid, right? It will return a true. Now, first of all, actually we'll not mark it here. Let's do it like this only. Okay. First of all, we'll visit the left subtree. Now, when we visit the left subtree, we want the height to contain the height of the left subtree completely. So we will first clear whatever the height has, right? We'll initially set height to be 0. Now we will assume that when the left subtree is completed, when is balanced for the left subtree is completed, the height will contain the height of the left subtree. So bool will contain the check, is left valid, is left balanced. So we'll call the is balanced on the root of left. We'll call the is balanced on the root of left, right? We'll call is balanced on root of left. So is the left subtree balanced basically? Now is balanced, we have got that. Now we have assumed that is balanced. When we call is balanced for a given node, the height variable will be storing the height of that subtree. So as it is storing the height of the subtree, let's save it somewhere. So left subtree height, right? Left subtree height will be equals to height, because it is storing, we are assuming that. And we have to make sure that it stores, right? Now let's go to the right subtree. So height again we'll set it to 0, because we want the height of the right subtree only. We don't want the left subtree, because now height stores the height of the left subtree. If we don't set it to 0, it will influence the height of the right subtree, which we don't want. We want the height of the right subtree. So we'll set height to be 0, and bool is right balanced equals to is balanced root of right, and int right subtree height equals to height. Int right subtree height equals to height, right? So we have computed left subtree height, we have computed left subtree height, we have computed right subtree height. We are also checking, is the left subtree balanced, is the right subtree balanced, right? We are checking both of them. Now the task is, before we return answer, we are expecting that is balanced should also set the height of the current node, right? Height of the subtree, current subtree. So what is the height of the current subtree? We should set the proper value. It should be the maximum of either the left subtree, either we can go on the left side or right side. So left subtree height, or the maximum of the left subtree height or the right subtree height, and +1, because the current node is also added to the subtree. So height of maximum of left or right subtree height +1. So now the height actually contains the height of the current node, right? So now we can definitely return. So if what? If it is balanced only when if is left balanced if the left subtree is balanced and then the right subtree is balanced, is the right balanced, and then the current node, it is balanced around the current node as well. How do we get that? The height difference, we already know the heights. So right subtree height minus left subtree height. If it is less than equal to 1, in that case we should return a true, right? We should return a true, otherwise we should return a false. Otherwise we should return a false. Okay, let's actually try to dry run this, right? Let's try to dry run this and see if it is actually working. So let's dry run on this example only. Let's dry run on this example, right? To see if it is actually, how does it actually work? Because we are setting height to 0, right? You might be freaking out, hey, we are deleting the height, how it might cause some problem and stuff, right? So let's figure it out. So let's say 8, right? Okay, let's have the height variable here. We start off at 2, right? 2 is not null, so we'll set the height to 0 and we'll call check BST for left. It will come to 1. 1 again will set the height to 0 and call for left, so it will come to 3. Then it will come to 7, then it will come to 8. Now from 8 it will go to null, it will set the height to 0 and come back. So the height at left subtree for 8 is 0. The height at right subtree, so left subtree is 0, right subtree is also 0, it will be 0. So this will return true. But before it returns true, it will also set the height, its current height, right? What was it? Max of left subtree height comma right subtree height plus 1. So left subtree height was 0, right subtree height is 0, so max is 0 plus 1, height becomes 1. So see, 8 has indeed a height of 1, right? So when we go to 7, we see it has a height of 1. So for 7, we don't have a right subtree, so the height is returned 0. So left subtree height for 7 is 1, right subtree height is 0. So difference is valid. So it will return true, but before it returns true, it will update its height. So its height will be, so height will be updated to max of left subtree plus right subtree, that is 1, 0. It is 1 plus 1, that is 2. Height will become 2 and it will come to 3 now. So the left subtree height for 3 is 2. Left subtree height for 3 is 2. Right subtree height, again there is no right node to be visiting, so it will be 0. It will be 0, right? So the difference will be 2 here and it will return a false. It will set the value, it will set its height to be 3 and it will return a false, right? It will return a false here. But let's actually go ahead, although it returns a false and it will become false in the upwards direction as well. But let's go to the right hand side. In the right hand side, now the height is again set to 0, right? Height is set to 0. So we have figured out the left subtree height is 3. So let's write it down here 3, right? We are storing that variable. Right subtree height, we are again resetting height to 0. We are going to 5, right? From 5 we are going to 9. At 9 the height is becoming 1, right? At 9 the height is becoming 1. So the right subtree height of our 5 is 1, left subtree is 0. So 5's height will be 2. So height of 5 will be 2 when it is returned, and it will return true as well. So the height of 5 becomes 2 and it returns true. Now here we check the height difference is valid. 3 minus 2 is 1. But the first one is false. That is, the left subtree is not height balanced. So it will return false now. Right? It will return false, and like that it will continue. Right? Like that it will continue. So this is the code. So let's try to run this and see if it is working. Okay, so it's expected. So let's submit and see if it is working. I think it will work. Yes, it's working. So yeah, this is the code. Let me know if anyone has any doubts with this code. So we are done with both the problems for today. We took around 30 minutes, right? We took around 30 minutes, maybe something more than 30 minutes. But again, like we have solved 2 problems in just 30 minutes, and I'm hoping that it's clear to everyone. So just like this is how you practice, right? Now you're getting in the habit. Over like next, let's say after 29 classes you'll be in the habit, so you can easily solve, like every day you can solve easily 3 to 4 problems a day, right? So you can easily solve all the 700 problems. So yeah, let me know if you have any doubts with this one. This was a bit tricky because we had to propagate the value upwards, and we found out a way that we maintained a variable, and we assumed that this variable would be like having the proper height whenever we recursively called, and to ensure that we also set the height to the correct height before returning a value, right? So let me know if anyone has any doubts with this. Anyone has any doubts with this? And you can find the practice problem for today in the description, so make sure you do that. I'm not sure how many practice problems are there, but I think there's only one practice problem for the day. Like, it will increase gradually for, like, let's say after this, maybe next day also you'll get 1-2 problems, but after that you will get 3-4 problems a daily, right, for practice. So make sure to practice them as well. So there is the practice problems are added. The added to the description. Yes, they're added to the description. Yep. Okay. Okay, you have done it already. That's great. So then you can enjoy the day off basically. But yeah, like, I think tomorrow also will be coming live, so do join there as well, and try joining every day, because then you will be in the habit and you can easily solve, like, just see like how many problems you're solving. Around 150 to 200 problems will be easily solving, right? So that will be help you, and definitely, and you will also get in the practice, right? Okay, no doubt. Thanks. Sure. Thank you guys. I'm hoping that no one else has any doubts. So yes, we'll see you in the next day.